And if you're wondering who the people in the background are, they're not very important. They're just the members of the research group that I'm working at. But it's actually their work, right? So these students, they're really smart students, and they work for this. And everything that I'm going to present today is really theirs, right? So it's their work. And what they're doing is they're building new defenses, making it harder for attackers to compromise our systems. And they're also developing new attacks, new types of vulnerabilities, try to discover new types of vulnerabilities. And why do we do this? We do this because I believe that the main problem that we have in security is that we no longer understand the systems that we build. They've become so complex that we no longer understand them. And by exploiting them, by finding new ways to exploit them, right, we learn a little bit more about, unexpected behavior that these systems can exhibit, right? And I think that's extremely valuable. It's also extremely valuable in a very direct sense of the word, right? So if you find a new class of vulnerability, it's actually translated into money, right? So large companies have these bounty programs. There's prices paid on in the more shady areas of the internet. It's a lot of money. Bounty programs of hundreds and thousands of dollars for a new vulnerability, new 0-day. That's a lot of money. Right? And it so happens that I need a lot of money because I need a new tariff. So what I thought, thinking of the bounty programs and all the smart students that I have in the group, what I thought I would do is, I would simply exploit the students, make lots of money, and get myself a new tariff. So I thought, let's do that. And when I started presentations long ago, someone told me you always have to start with 3 observations. But I couldn't think of 3 observations, so I'm going to start with 2 observations. So the first observation is that software exploitation nowadays, in contrast to what you read in newspapers, is actually super, super hard. Right? Exploiting a modern browser or a modern operating system is exceedingly hard because of all the defenses that are in place. This makes these 0 days so insanely valuable. Okay. The second observation is that we're in a very interesting era where physical attacks, side channel attacks, where people point with lasers at chips or, desolder chips and do all sorts of clever things, is meeting the world of software exploitation, right? So nowadays, some of these hardware bugs can be triggered from software. And that's very interesting. Now, why is this very interesting? Why would you care? Well, it's interesting because only a few years ago, 2014, I would start my first lecture on computer network security here at the Vrije Universiteit by saying, we have all of these security problems and they're caused by crappy software or misconfigured software, and we should really work on this. Nowadays, this year, when I just had my lecture on computer network security last week, I basically tell the students, look, even if your software is perfect, doesn't contain a single bug, perfectly configured, it's still vulnerable. And to see why, let's go back to traditional software exploitation, right? So if we have our software hardware stack with hardware at the bottom and, the user at the top, the traditional way of exploiting a system was you would find a vulnerability somewhere in this, in a program or in the operating system, a buffer overflow perhaps, and you would, misuse that to compromise the system. But as mentioned, this is now very, very difficult because of, address space layout randomization, non-execution bits and stack protection, control flow integrity, all sorts of complicated defenses that the vendors are throwing at their software to make it more secure. Okay, so this is super frustrating for our poor attacker because he's now left with the question, how do I get the primitives that I need to compromise these systems? And what primitive do you need as an attacker? Well, you need a read primitive and a write primitive, right? You need to be able to leak sensitive information, ideally, right? And you need a way to, violate the integrity of the system, maybe make the program do something that you would want it to do. And what read and write primitives can the attacker still obtain if we make the assumption that the software is perfect? Of course, the software is not yet perfect, but there's a lot of work towards this. Verification is just one of them. Okay, well, to see that, we should probably look at the entire history of popular computing. So the last 60 years or so, computing has had one goal and one goal only, I would claim, and that is efficiency. Everything was sacrificed at the altar of efficiency, and that includes security. One thing that we do, for instance, is we aggressively share. Right? We share everything. We share the CPU, we share memory, we share caches. There's all sorts of stuff that we share. And because sharing is super efficient, right? But I would claim that because of sharing, and this is a known result that's known, since the 60s, sharing is potentially susceptible to side channels. All the sharing that you do may lead to side channels. Okay, so my claim would be sharing is efficient, but really sharing is not caring, right? The more you share, the more dangerous things become. And we're going to have a look at that. What about, so this is what we're going to use as our memory read primitive, side channels. Okay, what about the memory write primitive? How do we write into the address space of a system where, beyond where we are supposed to write? If we can no longer do this in the traditional way. Well, here there are, things that we basically draw from, these physical attacks. There are hardware vulnerabilities that can be triggered from software. Okay, and those are really, really simple vulnerabilities. Just maybe you're able to flip a bit from a 0 to a 1 or 1 to a 0, but they're very powerful. These glitches from software are best exemplified probably by the row hammer vulnerability. So the row hammer vulnerability allows you to flip a bit in memory, right? DRAM vulnerability, memory chip. Okay. So once we have these two primitives, a memory read primitive and a memory write primitive, we go back to reliable exploits, and life is good for the attacker. Okay, so let's have a look at what that means, really. So for the past 10 years, most of the serious exploitation at the application level has been on the basis of code reuse. So you find a little snippet of code, a bunch of snippets of code in an existing program, and you make that do something new, something that the attacker wants. So to do that, what do you need? Well, you need to know where those program snippets are, right? So what is the address of a particular program snippet, so you can make the program jump to it and then do something that you want as an attacker, and also where the data is that corresponds to that. And once you know that, you can chain these things together into a malicious payload. This is what attackers do. So we need the addresses of code, we need the addresses of data as an attacker, and that's one of the things that we need. And the other thing that we need is bugs. We need bugs to find these addresses. We need bugs to divert the control flow. So we want to make this program do something that it shouldn't normally do, make it jump somewhere in the binary where it doesn't normally jump. So this is getting harder. And so the question we ask is, can we do all of this without any software bugs, right? So we have perfect software. Can we still do this? And the answer is yes. And I'm going to start with the hardware glitches, which is best exemplified, as I mentioned, by the row hammer vulnerability. And I'm not sure if you're all familiar with the row hammer vulnerability, but it was discovered quite recently, 2014, and it's a hardware vulnerability in memory chips, in DRAM chips. Okay, and it's a really funky vulnerability because it allows you to flip memory at locations where you're not even accessing that location. Okay, so if you look at a memory chip, a DRAM chip, it really is just, rows and rows of bits, right? That's all it is, right? And if you want to access a value in memory from your browser, from JavaScript, doesn't matter. You basically access one row of those bits, copy them into the row buffer, and then that gets sent to the CPU for processing. Okay. Now, these are just physical processes, right? So each of these bits is just a transistor and a capacitor, just, stuff that you find in your physics class. Okay. And a capacitor holds charge, but the charge leaks over time. Moreover, what happens if you access one row, right? So maybe this row, it has an effect because these chips, the bits are so closely packed together. If you access one row, a little bit of charge leaks from the bits in the adjacent row. Okay? And you can use this. So if you do this at a very rapid rate, so you access this row and then that row and then that row again and that row again, a little bit of charge leaks from this, poor bit location over there. And this accumulates. If you do this sufficiently often, the charge leakage accumulates to the point where a bit flips from a 1 to a 0 or a 0 to a 1. Okay? So you never accessed that bit location, that memory location, but you still managed to change it. It's kind of magic. Okay? And it's a probabilistic process. You have no idea which bit in that row is going to flip, but it's a repeatable process. So once a bit flipped once, if you do this again, it will flip again, right? That same bit. And that makes this a powerful thing in the hands of an attacker, because the attacker can now find out which bits are vulnerable in a computer system, right? And then give that to somebody else to use, and then see if you can flip the bit and do something bad. So it becomes a security problem. Let's have a look how that works. So Rowhammer was discovered in 2014 by the people at CMU at the time, and since then there had been a little bit of work of to try and exploit this. When we came into the game, we thought what we would want to do is see if we can exploit this in the state-of-the-art browser that we had in those days, right? So Microsoft Edge was more advanced in terms of defenses than any other browser that was available. It had control flow guard, which is a control flow integrity. It had address space layouts. So a lot of defenses were in there. And we thought, let's see if we can exploit Microsoft Edge without any assumption about software bugs or misconfigurations, and only from JavaScript. Okay? So this is what we're going to do. And the way we're going to do that, I'm going to sketch the attack first, so you have a rough idea of what I'm going to explain later, is we're going to use a side channel, which is known as memory deduplication, right, to leak the addresses of the data and the code, which I said we were going to need. And then we use this hardware glitch, right? So once we have this information, we use a hardware glitch, Rowhammer, flip a bit to make the control flow in the program, execute code that we want. Okay? And with that, we can exploit Microsoft Edge without any software bugs from JavaScript. And remember, we need to find addresses of code and data first. So that's what we're going to use our side channel for. And the side channel will get us an address, for instance, in the JavaScript engine of Microsoft Edge, right? So with Chakra, we just want to have a pointer, an address of some code there. Okay. And for that, like I said, we use this memory deduplication vulnerability. And memory deduplication is really simple. If you have a system with two processors running on top of an operating system, and there's some physical memory, some DRAM chips at the bottom somewhere, right? And let's assume that one of the processors has some data in memory, right? So a 4 kilobyte page that exists in memory. Of course, this will be really somewhere in the physical DRAM chip, right? So this data is there. If another process has the same page of memory, the same 4 kilobytes of memory, with memory deduplication, the system will realize that, wait a minute, these bytes are exactly the same. 4096 bytes are exactly the same. It's very inefficient to store this twice in physical memory. Let's merge them, right? So let's just store one copy and make both of these processes use that same copy. And of course, that's all okay as long as they don't modify it. Right? If it's read-only, it's perfectly fine. If they start modifying, of course you have a problem, because you don't want somebody modifying the data and then because of that, the data of somebody else changing, right? So if you modify this, if you write to this data, you have to reduplicate it, make a new copy, and this is slow. This is a slow process, because rather than just writing into, bits on a DRAM chip, now you have to trap into the operating system kernel, make a copy of the page, change the page tables, and then go back to user space, and then write into the DRAM chip. That is super slow. It's measurably slow. You can measure this even from JavaScript. Okay? The writes to those pages that are deduplicated take longer. Okay. So what does that mean? That means that you can now detect, you have a side channel to detect that somebody else, if you create some, a page worth of data with JavaScript in memory, and it gets deduplicated, because the writes get slower, right? You know that somebody else has the exact same data in memory. It's a side channel. You learn something about what somebody else has in memory. For instance, another process or another kernel. Okay, and we want to use this to leak this address of the code or the data. Okay, the code and data pointers. Now, let's go back to this, right? So if we have memory deduplication and we know exactly what data another process has in memory, and we recreate the exact same data and then write to that page after deduplication has merged them, it will be slower. But normally we don't know, let's say we don't know all the 4,096 bytes in exactly. We know all of the bytes except one, right? So how do we discover that last byte? Well, what we can do is simply make, 256 pages with different values for that one byte in memory, and then write to all of them and see which one was a little bit slower, right? So that means that that page had the right value for that one byte. So now we know this one byte. And that's what we're going to do for our address, right? So we're going to create a page where all of the content is known except for the address. Only the address is unknown. So then we can make lots of pages and guess the address, because that is the only page where the writing will be slow. Now, first of all, can we do this? Well, actually, from JavaScript, it's really simple, right? Because in JavaScript, at least in this JavaScript engine, the end of a function always led to exactly the same code. So if you wrote a JavaScript function, it would always end with this. And it's completely constant. It would always have trap instructions that run to the end of the page, right? So it would be entirely filled with trap instructions. And the only thing that would differ is there was a move instruction, another move instruction, and a jump instruction, right? Entirely predictable. Everything is predictable except this address here, right? We didn't know that address. So the entire page is known except the address. So what we can do as an attacker is simply create this page and then have a guess for the address. And if it's slow, if we write to that page, we know that it was the right guess, right? Of course, this is a little bit problematic because it's an address of 48 bits, right? So we create all known data, and then we have this one thing that is unknown. We simply guess for that, but it's 48 bits, right? So that's if we have to create 2 to the power 48 pages, that is a bit much, right? So we can't do it. But we control the functions that is being used for this, right? We are the attackers. We write the JavaScript. So we can control how large or small the functions are. So if we make the function a little bit smaller, we can make it such that only 1 byte gets mapped onto this page, or 2 bytes get mapped onto the page. So what we can do is, if we have 1 byte mapping onto the page, it's really easy. We make 256 pages with different guesses for the value of that 1 byte, and if it gets deduplicated, we know we have that byte guessed correctly. So then we try the next byte, and the next byte, and the next byte, and the next byte, until we have the entire address correctly. Okay, so we do something similar for the data. It's a little bit different, but I don't want to get into that. But if we know the addresses of the code and the data, what we can now do is create in memory, in our JavaScript array, the bytes that would exist in memory if there was a JavaScript object with a pointer to the method and a pointer to the data. Right? It's a fake object, doesn't really exist, but it has the right addresses there. Okay. Of course, the JavaScript engine is not aware of this object, and it will never call the method. But we know all the addresses. We now have broken all of the address space randomization. So what we can do is take an existing object, all the way on the left there, right? An existing object which has a pointer to it somewhere. Under the hood, there's all pointers, and use the row hammer vulnerability to flip exactly the right bit. And we know which bits are going to flip because we templated the memory first, saw which bits are going to flip. So we flip exactly the right bit to create the pointer now pointing to our fake object. And that means that when the JavaScript runtime wants to execute a method in the object on the left, It really is going to execute code that we want executed. Okay? And that means that we now have full control over the browser. Okay? And with that, you go and win a Pony Award. So we won a Pony Award for most innovative research with that. And we thought, that's great. I thought this was great because there's a Microsoft bounty program of 100,000 and I was going to cash in, get a terrace and everything. But Microsoft came back to us and said, yeah, well, it's a bit of an issue. It's a serious problem. Can you please not publish this? And I said, who cares about publications? But all my students said, we can't do that. We really need to publish. That's really bad. So, even though we observed the 90 days disclosure period, we got $0 for this. But that was bad. That was only the beginning. So we started thinking, what else can we attack? What else can we attack? And, okay, so we did dedupe as machina. The next thing we were thinking of was, can we do something in the cloud? Okay, so the next thing that I'm going to discuss is bug-free exploitation in the cloud, which uses the same primitives. So it uses a rowhammer vulnerability, so this hardware glitch where you flip a bit, and it uses the memory deduplication side channel. But now we don't do this as it uses memory deduplication, but not as a side channel, but rather as a way of deciding which memory a victim is going to use, right? So, and with that, as we shall see, we can compromise Linux KVM clouds without software bugs. So, let me explain this, right? So in a cloud you have, and you run KVM, right? So the virtualization technology in Linux, it has this feature called kernel same page merging. It's memory deduplication. It basically means that if there are two pages that are the same, they will be merged, just like in the previous case where this was on Windows. Okay, so if we have two virtual machines in the cloud, and one machine is owned by the attacker, and there is memory in the victim virtual machine somewhere mapped to physical DRAM, and there's memory in a memory page in the attacker virtual machine mapped into physical DRAM. If those pages are the same, they will be merged. Okay, so that means that both of them again use the same physical memory. Now, what we're using this time is the property that we decide which page is going to be used, which physical memory is going to be used. So what we're going to do is we're going to first find one page where there's a bit flip, a rowhammer vulnerability. We've, simply hammer everything until we find a bunch of bit flips and we say, oh, this page has bit flips, right? And then we're going to make sure that the data that is going to be deduplicated is going to be on this physical page, which we control anyway, right? So we can put anything we want there. And that means that if the deduplication kicks in, the victim also uses this vulnerable page with bit flips on them. Okay? So now we determine the physical page and we can hammer it. And that means that a bit will flip on the page. Now, the question is, what can we do with this? What can I flip to gain access to a victim virtual machine? And another question is, we need to have a page that is exactly the same as the page of a victim. Which pages do we know to be the same? Okay. So here's what we did. We simply tried to SSH into the victim machine, right? Just an SSH. And of course, we're not allowed because we don't have access to this machine. It'll never work. But what the victim machine will do, so even though it's not allowed, is it will check on Linux the authorized keys file, right? This is just a file on desk which says, this is the key of the Linux administrator for this machine, right? And what this will accomplish is that this file will now be in memory. So there's a page in memory with the key, the public key of the administrator. Okay, and this is a public key, and public keys, by definition, are not secret, right? You can just go to GitHub and look at people's public keys. So we now know this public key is on this vulnerable page, right? So it's here, and we can hammer it, and that means we can flip a bit in the key, the public key of the administrator, right? So we hammer away, and a bit flips. And, these keys are chosen, RSA keys, right? They're chosen not arbitrarily. They're chosen because they are really, really difficult to factorize. Now, if you flip only a single bit in one of those public keys, and I don't understand the cryptography behind this because we're not cryptographers, but if a single bit flips in one of these keys, all of a sudden they become really easy to factorize, right? And that means that we can break this, change this key, and then find a private key that corresponds to this key. Okay? We can find a key that corresponds to this broken public key. And that means we can now just use the SSH again with our, new private key and enter it into the victim machine. And let me just see if I can, in the interest of time, I'm going to skip the follow-up of that. Okay, so this is Ben and Kaveh breaking the internet, so they could actually not just compromise the other virtual machine, but they could also make the other virtual machine, you get all of its updates and all of its new installation of packages coming from our machine, right? So we made sure that all the updates from the victim would basically be retrieved from our machine. Fantastic stuff. We thought this would get us make us really rich. In reality, we got zero money for this, right? So this was not interesting enough. Super frustrating. So the next thing we did was try this on ARM processors, right? Because mobile phones, such a huge market, people are going to care. We thought, let's do bug-free exploitation on phones, on Android phones. Okay. And this was work by Victor van der Veen, and Victor was looking for a project, and we said, why don't we try this on mobile phones? And he tried, and none of the techniques that we had on x86 worked. And this is not for lack of trying. We tried really, really hard, and we did not get anywhere. And to make matters worse, Victor went on a conference and then on an internship. So we went to Barbados and then to Santa Barbara, which is this really nice beach town on the west coast. But he said, don't worry, I will work on it from there. But I, to be honest, I was a little bit worried because Victor sent me a picture, right? This is what he was doing there. And, a week went by and there were no results. And, 3 weeks went by, no results. A month went by, nothing, right? So we got absolutely nothing, and he kept sending us pictures like this. So I sent an email to everybody in the project, and this is the actual email. Just adding Victor to this list, and he's working in UCSB, getting bit flips, and from now on, he's not allowed to go surfing until he gets a flip. 2 days later, bit flip. Just showing management skills here. And then immediately afterwards, Victor sent me a picture, and this was... Anyway, so this was kind of cool. We were able to exploit these phones from JavaScript, completely compromise the phones. It won a bunch of prizes, including a Pony Award. And then we contacted Google about this with a list of suggested mitigations. And this was 91 days before we were going to publish this. And they said, that's really cool. You definitely deserve a bounty for this. But please, can you publish this at another conference? And everybody said no. And, so that didn't work. What if we give you money? And they still said, oh, no. It's violating the academic process. And then they said, what if you obfuscate the paper? And in the end, we got $4,000 for this, for a critical issue. Simply because we didn't have in our paper any of the phones that were in the reward program explicitly. So we fixed that, and immediately afterwards, of course, those phones were also in that system. But, we got $4,000 for, 4 months of work by 9 people. It was not going to get me a terrace. But we were not going to give up, so we tried to do this. Oh, this was not from JavaScript, I should say. We were going to try this from JavaScript, which I don't want to, because a lot of people doubted that you could actually do this from JavaScript. So we tried this. I'm not going to explain the attack. I just want to say that the way we did it was not by using the CPU. It's not just the CPU that is a problem, but on modern phones, you have, besides, your normal CPU, your normal cores, you have your GPUs, right? Your graphics processing units. And they are nowadays completely accessible to JavaScript via WebGL, right? So, and WebGL gave us a lot of accesses to memory that we couldn't get via the CPU, and it allowed us to exploit, modern browsers on mobile phones from JavaScript, and it got us no money. So the next thing we thought, if they don't care, if the consumer devices don't care, the client devices don't care, what about the servers? Can we do this on servers? So, we're a little bit further in the timeline now. We've done every device on the client side that we could think of. What about servers? Can we attack servers from across the network? So a remote attack. All of the attacks that we've seen so far assumed that we had JavaScript or something similar running on the victim machine, flipping bits and then, exploiting the system. But what if we don't have that? Can we actually do this remotely? And again, there's no time to explain this, but we had this attack called Throwhammer, where you actually, across the network, you send a lot of data to a server, and because the data gets stored in memory, it has a lot of memory accesses, and bits will flip. And we showed that you could, compromise, say, a memcached key value server, and exploit software. Got us no money, obviously. The next step we thought, because people said, on servers, we don't really care, because we have much better memory. We don't have this vulnerable memory. We have error-correcting codes. What could go wrong? So we thought, let's try ECC memory then. So can we with ECC memory? So ECC memory has this property that if a bit flips, it's fine because there's error correcting code and it will automatically flip it back, right? That's what the ECC stands for. So you have to flip multiple bits, not 2 bits though, right? So if you flip 1 bit, it will be corrected. If you flip 2 bits, the machine will crash. Right? That's not what you want. It's a denial of service attack perhaps, but it's not what you want. So you have to flip 3 bits and you have to flip the right 3 bits, right? To make sure that the error is not corrected and not detected, right? So it's really, really complicated, but it turns out that you can still do this. We did a lot of reverse engineering to find out how all of this worked. Found a new side channel, and we have this attack that you can actually launch at an ECC server. And here we are, right? So we got a distinguished paper award for this, but you can see how happy we are because we're going to get super rich now, right? The vendors are going to pay us an enormous amount of bounty, and we got 0. This is not going well, right? I was never going to get a terrorist this way. So maybe we should look at the other side and forget about these bit flips and maybe see if we can work on the side channels, leak more information. Okay, so that's what I'm going to talk about in the remainder of this talk. So we're going to talk about the side channels that's what I'm going to talk about in the remainder of the talk. And I'm going to skip a number of these attempts that we made, right? So we have in total 10 attacks in this full presentation, and I'm going to skip 7 to 9, so 3 of them. Just want to say that we didn't get any money. But I thought, last year I thought there's actually a lot of, publicity about these new kind of speculative execution attacks. And this is all over the news. It was on CNN. I watched it on CNN. I thought, people clearly care about this. So let's see if we can do something in this space. And this is the last thing I want to present. It's something that was, in the news in this country and also other countries quite massively. It's Riddle, right? It's rogue in-flight data loads. And it's a vulnerability in the class of, Meltdown and Spectre and Foreshadow, right? So this was all 2018. There were a lot of these attacks, and they're super scary, right? And this was one of those, and it's the only time that my research team made it to the front page of the newspapers. So this is the picture on the newspapers, and at the time 2 of the members were not there. So this is Cristiano and this is Jorgi, so they were also part of the team. And what we did in in this, let's see if this works. So what we did was use the vulnerability to leak sensitive information. And here's one example where initially you see that that some user is trying to access the etc shadow file. On a Unix system, this is where all the hashes of passwords are stored. Super secret, you're not allowed to touch this as a normal user. And you can see that, right? So the first line, he tries to show this etc password file, and it says permission denied. Okay, because you're not super user. If you do this as super user, so with sudo etc shadow, then you can actually observe the content of that shadow file. So you can see that here there's one line of this shadow file that is shown. It's the root entry. So it has the hash of the password for the root user. This is what you're after. This is what you want as an attacker. Okay, but you can't access it except if you see, here there's oh, you don't see the pointer. You see that the attacker runs hack password, right? Hack password without being super user. So it's not with the sudo command. So it's a regular user, and he types hack password and then root : because he's after the root user. And you see that it very gradually finds every byte in this etc shadows entry for a root user. And this is nowadays really fast. You can do this within a minute. Okay? So how does that work? The vulnerability is called rogue in-flight data load. And this is really what it is. There's data in flight on your processor all the time. And sometimes Intel doesn't take good care of this data. Okay? So it's a class of speculative execution attacks. It's not just one attack. There's several aspects to it. It's a class of speculative execution attack that Intel now calls microarchitectural data sampling. And just to emphasize what you can do with this, you can leak data from a normal process without any privileges, and you can leak data from another process, right? Another hyperthread on the same core, but also from the kernel, from other virtual machines, from the hypervisor itself, and even from super secure enclaves, such as protected by SGX. Okay. Moreover, you can do this from the browser, from JavaScript. Okay. So this is kind of bad. And it's different from the previous attacks, Meltdown, Spectre, and Foreshadow, in the sense that all of these previous attacks used addresses. You can speculatively leak data using addresses, and if you have, the right sort of address, you will get, some part of the information. But it also means that you can mitigate this by focusing on the addresses, right? All of the mitigations simply focus on these addresses. For instance, for Spectre, you can leak addresses, at least one variant of Spectre. You can leak information beyond a buffer boundary, right? And that the mitigation is simply make sure that all the addresses are inbound, right? So make sure that they're inbound. For Meltdown, you can leak data from kernel addresses. So you simply make sure that there is no kernel addresses in your address space anymore. So no kernel data in your address space anymore. So all of these mitigations are spot mitigations for these particular things. Okay. So a bunch of these mitigations, they're all, all the mitigations that we've seen so far are spot mitigations. So they're not super structural and not complete. Okay. So Riddle doesn't use any addressing at all. It doesn't care about addresses. It simply leaks information that happens to be floating around your CPU. None of the mitigations work. And we don't believe in logos, so we don't have a logo for Riddle. What we do have is a lot of CPUs. So we bought every single Intel CPU since 2008, right? And some of them are hard to get. You have to go on eBay or Marktplaats or so and get some old Intel CPUs. So we bought every model since 2008, and we bought 2 IKEA racks, right? So these are actual IKEA racks in our students' room that to store all of these machines. We also bought a bunch of AMDs and ARM processors, and Riddle works on all Intel processors since 2008. Okay. Doesn't work on AMD, doesn't work on ARM. Okay. So all of the Intel, these are some of the Intel processors that we tried, and right after we submitted the paper, we actually got a new Intel processor, the Core i9-9900. And that had, in hardware, in silicon mitigations against the previous speculative execution attacks. So we thought, does that work? And sure enough, Riddle simply worked without any problem. Okay, so it works great on Intel, doesn't work on AMD, doesn't work on ARM. That's not to say that there, there's probably other vulnerabilities on ARM and AMD, but just not this one. And where we're leaking from is important. So we're leaking not from the usual places. So the usual, everybody knows that CPUs have caches, a level 1 cache and a level 2 cache, where data is temporarily stored. But what very few people know is that there are lots and lots of other places, lots and lots of other buffers on the processor where data is temporarily stored. Okay? One of them is this thing called the line fill buffer. There's a bunch of others, the store and forward buffer and the load port. Okay, but let's focus on only the line fill buffer in the interest of time. So line fill buffers, if you look at the documentation, and there's very little documentation, we read about, or the students, I should say, have read about 50 patents, right? This is probably the worst job that they've ever had. So they read 50 patents. And it says that, these line fill buffers are used for asynchronous memory requests, load squashing, write combining, uncached memory. Who knows, right? So who knows what they all mean? Let's just look at one of them, asynchronous memory requests. What does that mean? Well, it basically tries to use the cache more efficiently. Okay? So it's a central buffer between the execution units here and the caches to improve memory throughput. So, for instance, if you have a cache miss, right, what you could do is simply go and look for the memory, the data in memory, and wait until you get that, and then give that data back. But that's really inefficient because you're blocking the cache. Nobody else can use the cache in the meantime. So what they're doing instead is they say, let's allocate one entry in this special buffer, this LFB, the line fill buffer, right? And that can deal with this memory request that had a cache miss, get it from memory, get it in the line fill buffer, and then later on I'll put it in the cache. So that's much more efficient because in the meantime you can use the cache for other things, right? So that works really well. Now, unfortunately, Intel is really sloppy with that cache. So the cache may contain data, right? So may contain data that have nothing to do with your program. Could be containing data from, completely different program, from the kernel, from other processes, and so on. And in certain cases, namely under what is sometimes referred to as speculative execution, although it's a little bit of a sloppy term here, in some cases, you actually get the data from somebody else. Right? This is insane, but it's fine because, as Intel sees it, right? Because, even if you get that data, the results will never be visible, right? So they will squash those results. It will realize, like, oh, that's not your data. I'll remove those. And it's fine. But there are still traces. There are traces in the cache that allow an attacker to see what that data is. Okay, so the attack that we showed earlier basically does the following. You have a victim VM with this etc shadow file, and you have an attacker VM, and there's this line fill buffer that is shared by the victim and the attacker. And we have an SSH client connecting to the victim VM. Now, because of that, the victim VM will load this etc shadow file in memory. And this will go through this line fill buffer. Initially, it's a cache miss, so the line fill buffer will take care of this. It's in the data is in the line fill buffer. And then we run this riddle code. It's a secret little code, and leak the data. Now, Intel tells you this is really, really difficult to exploit. It's a really complicated attack. It actually, what is behind it is really complicated. But the attack is one line of code. Literally one line of code. It could be this one. There could be actually other lines of code also that leak the same thing. In this case, we simply, I don't know whether you're familiar with the C programming language, but in this case, it's just a dereference of a null pointer. Right? That's the only thing you need to do to get somebody else's data. Right? So it's not difficult at all. Okay, and then you use traditional methods to, infer what that data is. The only problem with this attack is that it's not that it's difficult to get somebody else's data, but you're getting too much of it. You're getting all the data, right? And figuring out what data is interesting and what data is not interesting is really the challenge here. Okay. So, in the case of the etc shadow file, and in many other cases, it's actually trivial. So we know part of the data that we're after, and we just want to figure out the rest of it. For instance, in the etc shadow file, we're looking for the entry for root : So we know that the data starts with root : So what we're doing is the same thing that the people do in DNA sequencing, sequence alignment, where you have all of these bits and pieces floating around, and you just have to match them up and try to figure out, okay, this is my genome, for instance, right? It's my DNA. We do something similar. We know that it has to start with root, so we're looking for data in this line fill buffer that starts with root : Okay? And then when we see data drinking from the fire hose, and we're seeing data that doesn't match that, we know that this is the wrong data. But if we do get data where we actually see partial match, the first 4 characters or 5 characters have the same beginning, then that's probably a match. Right? So we know that we then take the next byte and we say, oh, that's the right byte, that's the next byte. Okay. And then we see more data and we say, oh, that's no good. And then we see data again which starts with, again, the same prefix, and we take the next character. Right? We do the same, partial guessing for all of these things until we have the full root password, hash of the root password. Okay. So we disclosed this to Intel in September 2018. On December, we heard that there were some other finders. So Intel told us there were 3 other finders of this vulnerability. We thought, that's too bad. 2 of them were from the commercial world, from industry. One of them was an academic, so we invited him on our paper. And then, guess how much we got for this in terms of a bounty program? 100,000. We got 100,000. Yeah. I got a terrace. Right? And then the university told us that all the bounty money goes to the university. Anyway, so the disclosure process was a really, bizarre procedure with Intel telling us, one thing and then changing the story after a while. And like I said, we found other finders in December, and then just before the publication of our paper, Intel told us, wait, there's actually, a zillion other finders, right? So, and it's really complicated now. If you want to know the full story, go to mdsattacks.com. It's an interesting story. So conclusion. Intel CPUs are vulnerable, and Intel really doesn't take care of its data carefully. And if you have Intel CPUs, you really should apply these patches if you have, different security domains running on the same machine. If you have different security domains and hyperthreading, turn off hyperthreading. It's expensive, but it's worth it. If you really don't trust the other domains, hyperthreading is vulnerable. Even with whatever Intel tells you in its advisory, turn off hyperthreading. There are other reasons. Sharing is not caring. The other thing is that I still don't have a terrace. We suck at bounty programs. Attackers need read-write primitives, and for write primitives, they can use glitches. We saw row hammer vulnerabilities that allow you to flip bits, and even if it's just a single bit, it's enough for an attacker to get full compromise of your entire system. For read primitives, we have many side channels, right? So there's many of them, including this new riddle attack. And these vulnerabilities change everything, because even if your software is completely formally verified, it's no longer secure. And I want to part with this. The vendors get this wrong also, right? So Microsoft in 2016 had this statement, really proudly said that at Black Hat 2016, it said, thanks to our mitigation improvements, since releasing the Microsoft Ads browser 1 year ago, there have been no zero-day exploits targeting Microsoft Ads. On that very same day, we had a talk at that very same conference saying, there's an exploit of the latest Microsoft Ads browser with all defenses up and not having any software vulnerabilities at all. All right. Thank you very much.